Not everyone who changes the world knows they are changing the world. Jack Kilby did not know. He only wanted to solve a problem. Born in Missouri in November 23, son of an engineer, a calling in his blood. Grew up in Kansas, always searching for answers, with a simple dream that time would not flood. He wanted to understand electricity and transform the world for good. Jack St. Clair Kilby, November 8th, 1923. He served in the Second World War as an electronics technician, studied electrical engineering in Illinois and Wisconsin, worked for years building ceramic components for circuits. In 1958, he joined Texas Instruments as a new employee, and because he was new, he had not yet earned the right to vacation. Everyone went away to rest that summer, and he stayed behind with nothing left to do. But in that silence, a question began to rise, a question that would change the way I grew. If everything is born from the same material, why should each piece be born separately too? The transistor was one piece, the resistor was another, the capacitor too. Each component manufactured separately, then someone had to put it all together by hand, soldering one piece at a time. And Kilby asked, what if the resistor and the capacitor could also be born inside the same germanium? Kilby took a small bar of germanium just over 1 centimeter long. Instead of assembling separate pieces, he drew each one of them directly into the material. Transistor, capacitor, and resistor, all born from the same piece. Then he connected everything with thin gold wires suspended in the air. The engineers called those wires flying wires. Inside a small bar of germanium, a new world began to grow, where separate pieces once existed. Everything was born together below. On the 12th of September, 58, the paradigm began to show. Kilby connected the germanium to an oscilloscope. He pressed the button. A wave appeared on the screen. The circuit worked. Resistor, capacitor, and transistor, all made of the same material, all on the same chip, all working together. Kilby said years later, if I had known I would be showing this for the rest of my life, I would have made it a little neater. Every limit ever found, someone searched for another way. Every unanswered problem gave birth to a new idea. The story of learning is the story of never stopping. More than 60 patents in all. The pocket calculator was one of them. The thermal printer was also born from his hands and from his vision. In 2000 came the Nobel Prize in Physics, 42 years after the first spark's ignition. Kilby said, when receiving the Nobel in 2000, it was a completely unexpected surprise, but a very pleasant one. It is gratifying to see the committee recognize applied physics, since the prize is typically given for basic research. Robert Noyce died in 1990. The Nobel is not awarded to those who have already passed, but both are remembered together as co-inventors of the integrated circuit. Jack Kilby died on June 20th, 2005 in Dallas at 81 years of age. He did not change a single component. He changed the way of thinking about electronics. And that way of thinking is inside every computer, every phone, every television, every car, every electronic device in the world. It all began in that summer of '58, in that empty laboratory, in that small bar of germanium. On the 20th of June 2005, Kilby left his legacy carved in time. From an empty laboratory in a summer long ago, a transformed world began to climb. A small chip opened the path for the future by design. But the story of the integrated circuit did not end with Kilby. The prototype worked, but the flying wires were too fragile for mass production. It was possible to make one, but not millions exactly the same. Someone still needed to find a way to manufacture integrated circuits in silicon on a flat surface, without any wires suspended in the air, millions of times with the same quality. That is the second part of the story. In the previous part, Jack Kilby proved it was possible. Transistor, resistor, and capacitor, all built on the same piece of germanium. But the prototype had flying wires, thin gold wires arched in the air, too fragile for mass production. And it was made of germanium, not silicone. Someone still needed to solve two problems at once: build them in silicone, and without any loose wires in the air. Born in Geneva on the 26th of September 1924, a physicist by vocation, two doctorates, Geneva and Cambridge, he crossed the ocean in search of a mission. Worked with Shockley, the father of the transistor, and joined the 8 engineers who founded Fairchild Semiconductor. John Amédée Hoerni, September 26, 1924. Born in Geneva, Switzerland. 2 doctoral degrees in physics, University of Geneva and Cambridge. He came to the United States to work with Linus Pauling at Caltech. Then he was recruited by William Shockley. But Shockley's erratic behavior led Hoerni and 7 other engineers to leave the laboratory in 1957 and found Fairchild Semiconductor. History called them the Traitorous 8. It was at Fairchild that Hoerni had the idea that solved Kilby's problem. The Mesa transistors had one problem: the exposed junctions kept failing without end. Contamination and leaking current, too unreliable to trust or to depend. Hoerni looked at the oxide layer, and there he saw the solution. The transistors of that era were the Mesa type. They had their junctions exposed on the surface. This caused contamination and current leakage. The conventional wisdom said, remove the oxide layer after fabrication. Hoerni disagreed. On December 1st, 1957, he wrote the idea in his notebook. What if the silicon dioxide layer stayed over the junctions to protect them from contamination? The idea sat in the notebook for more than a year, while Fairchild struggled to survive. Every limit ever found, someone searched for another way. Every unanswered problem gave birth to a new idea. The story of learning is the story of never stopping. In January '59 he filed a patent. In March he demonstrated the planar transistor at last. Built on silicon, protected by oxide. No loose wire, no exposed junction in the past. Fairchild launched it commercially in April '60, and the electronics industry embraced it worldwide. The Hoerni planar process worked like this. A slice of silicon receives a layer of silicon dioxide. Windows are opened in that layer using light and acid. The transistor components are created inside those windows. The oxide layer stays over the junctions, protecting them. The transistor becomes completely flat. No mesa, no wire, no exposed junction. One historian called it the most important innovation in the history of the semiconductor industry. The Hoerni planar process is still the foundation of every modern chip manufactured in the world today. Hoerni died on the 12th of January 97 in Seattle at 72 years of age. Less famous than Kilby and Noyce in the story, but his idea lives inside every modern technology. Without the planar process, there would be no integrated circuit, nor the digital world humanity knows today. John Hoerni died on January 12, 1997, 72 years old, less famous than Kilby and Noyce. But without the planar process, Noyce's integrated circuit would not have been possible. And without Noyce's integrated circuit, there would be no modern chip. Hoerni solved the problem of the flying wires. Hoerni solved the problem of germanium. But someone still needed to connect the components without any wire, neither gold nor aluminum outside the silicon chip. That is the third part of the story. In the previous part, John Hoerni solved two of Kilby's problems. The planar process replaced germanium with silicon, and the oxide layer protected the junctions, no loose wires in the air. But one problem remained: how to connect the components inside the same chip without any external wires. Kilby had used gold flying wires arched in the air. Hoerni eliminated the wires. But who would connect the components inside the chip itself? Born in Burlington, Iowa, on the 12th of December, 1927, son of a minister, studied physics at Grinnell and then at MIT. Worked with Shockley, co-inventor of the transistor. Was one of the 8 who founded Fairchild and became its research director. An inventor. Robert Norton Noyce, December 12, 1927, Burlington, Iowa, son of a congregational minister. Studied physics at Grinnell College and then at MIT. Brilliant, charismatic, a natural leader. Noyce and Hoerni were among the traitorous 8 who founded Fairchild in 1957. Noyce was the director of research. On January 14, 1959, Hoerni presented the planar process to Noyce. 9 days later, Noyce had the idea that changed everything. On the 23rd of January 59, Noyce opened his notebook and wrote the solution: how to connect the components inside the chip using thin metal deposited across the oxide layer. No external wire, no flying wire, just metal over silicon. The great invention. In the Fairchild patent notebook on pages 70 and 71, Noyce wrote, "It would be desirable to make multiple devices on a single piece of silicon, to be able to interconnect the devices as part of the manufacturing process and thus reduce size, weight, and cost per element." The method was to use Hoerni's silicon dioxide as insulation and deposit thin strips of aluminum directly over it to connect the components. No flying wires, no gold wire arched in the air. The connections were born inside the chip itself. Every limit ever found, someone searched for another way. Every unanswered problem gave birth to a new idea. The story of learning is the story of never stopping. Noyce filed the patent on the 30th of July 59. In April 61, it was finally granted. The dispute with Kilby reached the highest court, and history recognized them both. Both were recognized as co-inventors of the circuit, and modern electronics was born from their work. Noyce's patent was granted on April 25, 1961. The dispute between Fairchild and Texas Instruments lasted years. In 1966, the companies reached an agreement. Both would license the technology. Kilby and Noyce came to be called co-inventors of the integrated circuit. In 1970, the Supreme Court confirmed Noyce's priority. But historically, both are remembered together. Kilby for the concept, Noyce for the method that made the chip possible at scale. Noyce founded Intel with Gordon Moore in '68, the company that would put the processor on a single die. He died on the 18th of June of '90, before seeing the Nobel that might one day come by. But every chip in the world carries his idea of connecting everything inside. Robert Noyce died on June 18, 1990, 62 years old. Had he lived 10 more years, he would likely have shared the Nobel with Kilby in 2000. Noyce and Gordon Moore founded Intel in 1968. Kilby proved the concept. Hoerni created the process. Noyce connected everything from within. 3 engineers, 3 problems, 3 solutions. None of them knew they were completing each other's work. That is the 4th part of the story. Three engineers, 3 different problems, 3 solutions that no one knew would come together. Jack Kilby stayed alone in a laboratory in the summer of 1958 and proved it was possible. Gene Hoerni wrote an idea in a notebook in December of 1957 that would solve how to manufacture it. Robert Noyce opened his notebook on January 23rd of 1959 and showed how to connect everything from within. None of them knew they were completing each other's work, but together, they changed everything. Kilby showed me I could be born whole. Hoerni gave me the right way to grow. Noyce taught me how to connect from within. 3 answers to 3 parts of the same journey. Each one overcame the limits of the one before. And I kept growing smaller to expand my reach. Before the integrated circuit, a computer filled an entire room. The ENIAC of 1946 weighed 30 tons, occupied 170 square meters, and used 18,000 vacuum tubes. The integrated circuit opened the path to the microprocessor, and the microprocessor would place the brain of the computer on a chip the size of a fingernail. From an entire room to a silicon chip, and from that chip billions of transistors would grow. From 30 tons to fit between 2 fingers, from armies of technicians to a handful of engineers. The revolution did not come all at once. It came piece by piece, step by step, slow. The integrated circuit was not a single invention. It was a convergence. More than a century and a half of discoveries about electricity prepared the capacitor, the resistor, the diode, and the valve. The valve prepared the transistor. The transistor prepared the integrated circuit. And the integrated circuit prepared what would follow. Each generation overcame the limits of the one before and opened a door they did not know it was opening. Searched for another way. Every unanswered problem gave birth to a new idea. The story of learning is the story of never stopping. Kilby received the Nobel in 2000. Noyce had left 10 years before. Hoerni died in '97 without recognition. But their ideas live inside nearly every modern device. In phones, televisions, and cars around the world. Their inventions are woven into modern life. Jack Kilby died on June 20th, 2005. Robert Noyce died on June 18th, 1990. Jan Hoerni died on January 12th, 1997. None None of them built a computer. None of them imagined a mobile phone. None of them spoke of artificial intelligence. They only solved the problems in front of them. But each answer opened a door that the world would walk through decades later. One proved that I could be born whole. Another gave me a reliable way to grow. A third showed me how to connect from within. And I kept growing smaller, stronger still. Each door opened revealed a new question, and the story never stopped moving forward. While the integrated circuit was beginning to change the world, another invention was waiting for its time. It had been created at Bell Labs in November of 1959. Two immigrant engineers, one from Egypt, one from Korea. The industry did not recognize its importance for years. But it would be that invention that would make it possible to place not thousands, but billions of transistors inside a single chip. That is the next part of the story.